Today we discuss on the pre-predator Lotka-Volterra model, semester 5, unit 2, DSC A1 paper. First, we discuss general pre-predator system. Consider two populations whose sizes at a reference time t are denoted by xt and yt respectively. The functions x and y might denote population numbers or densities, number per area, and are taken to be continuous functions. Changes in population size with time are described by x dot equivalent to dx dt and y dot equivalent to dy dt respectively. And a general model of interacting populations is written in terms of two autonomous differential equation, first order nonlinear differential equation, x dot equal to x into function f of xy, and second equation y dot equal to y into another function g of xy. This system 1 is autonomous differential equation, first order nonlinear differential equation. Here autonomous means in the right hand side of the system 1, time t does not appear explicitly in the right hand side of the equation 1 and equation 2, second equation and first equation. The functions fxy and gxy denote the respective per capita growth rates of the two species, because this x dot from the first equation 1 by x dx dt equal to f xy. So obviously 1 by x dx dt gives the per capita growth rate of the species x, species with density x. And similarly 1 by y dy dt equals to gxy. So gxy is the per capita growth rate of the species density y. It is assumed that df dy is negative and dg dx is positive. Taking x and y as the prey and predator densities at time t respectively. So here we denote x is the density of prey and y is the density of predator at time t respectively. Also taking this function f equal to some function h of x minus y by x into phi xy, and g function equals to psi g function of xy minus e. Then system 1 becomes x dot equal to x into hx minus y into phi xy, and second equation y dot equal to minus E into y plus y into psi xy. This system 2 is the classical pre-predator model where age x is the per capita intrinsic growth rate of prey in the absence of predators, and E denotes per capita death rate of the predator in the absence of prey, and phi function denotes functional response, that is the amount of prey biomass consumed per predator per unit time. Amount of prey biomass consumed per predator per unit time, this function is phi. And another function psi is the numerical response, that is per capita predators growth rate by consuming the prey. Also, phi equals to theta into psi. So phi is the functional response and psi is the numerical response. So relation between this phi equal to theta into psi, where 0 less than theta less than equal to 1. And this theta denotes the food conservation efficiency of predator. Now we discuss the particular model on pre-predator model system, um, famous model, Lotka-Volterra model. The Lotka-Volterra equation, also known as the predator-prey equations, are a pair of first-order nonlinear differential equations, frequently used to describe the dynamics of biological systems in which two species interact, one as a predator and other as prey. The system is given by dn dt equals to Rn minus Cnp and dpdt equals to Bnp minus Mp. This is the system Lotka-Volterra model, first equation and second equation. This n denotes the density of prey and p is density of predator. Both depend on the time t. And R, C, B, M are some parameters in positive constants. R, C, B, M are positive constants. Now, from these equations 1.2 and 1.1 and 1.2, and the assumptions for this model are: first term Rn on the right hand side 1.1 implies that the prey will grow exponentially in the absence of predator. So if put p equals to 0 in the first equation, p equals to 0, then this equation converts to dn dt equal to Rn. So dn dt equals to Rn. So dn by n equals to R into dt. Integrating on both sides, we get this ln n equals to rt plus some function log c, ln c. So from this we get this n equals to exponential c into exponential rt. So when p equals to 0, p equals to 0 means absence of predator. So growth of the prey, that is n exponentially growth. So n is equal to some constant c into e to the power rt. So absence of first assumption of this model is that when predator is absent, then the growth of the prey will be exponentially growth of the prey in absence of predator. And the second assumption, the from the first equation 1.1, the second term is minus CNP. So from first equation, this second term is minus C into N into P. So this term minus CNP on the right hand side of 1.1 describes the loss of prey due to predator. Loss of prey due to predators, and this loss is assumed to be proportional to both the number of prey and the number of predators. So this loss is assumed to be proportional to both the number of prey and the number of predator. Resulting in what is often described as a mass action term. So, the effect of predation is to reduce the prey's per capita growth rate. Effect of predation, due to effect of predation, which reduce the prey's per capita growth rate. Prey's per capita growth rate means 1 by n dndt. So effect of predation, due to effect of predation, the per capita growth rate is reduce the prey's per capita growth rate, and this term is minus. So this is the from the first term we get from this first equation. So 1 by n dn dt, 1 by n dn dt one by n from the first equation dn dt equals to from the first equation, and this equals to r minus cp, r minus cp, r minus cp, c into p. So this is the per capita growth rate of the prey. This is the per capita growth rate of prey. This term minus, so this minus present in the present minus sign, present in presence of the sign minus sign. So due to effect of predation, this is the per capita growth rate of the prey reduces. So second assumption of this model is that due to the effect of predation, reduce the prey's per capita growth rate, and due to the second term minus C and P, where C is a positive constant. Next, third assumption, the prey's contribution to the predator's growth rate is BNP. Prey's contribution to the predator's growth rate. Predator's growth rate is BNP. Prey's contributions from the second equation of this model. Second equation dp dt equals to BNP minus MP. So this dpdt is the predator's growth rate. So predator's growth rate effect of the term BNP. B is positive constant, N is the density of prey, and P is the density of predator. So this is the when dpdt growth rate increases, then BNP increases, and this minus MP due to the term minus MP. So this term for this presence of this term, second term, this the growth rate of the predator reduces because this negative sign is here. So third assumption is that the growth rate of predator uh, is due to the term in the second equation in the term B in B. So third assumption is that uh, it is the proportional to the available prey as well as to the size of predator's population. So it is proportional. It is means predator's growth rate. Predator's growth rate means DPDT. So DPDT, predator's growth rate is due to the proportion is proportional to the available prey, that is N, and as well as the size of the predator, that is P. So DPDT increases when P and N B into P into N. For predator's growth rate uh, is proportional to the available of prey and to the size of predator populations. And fourth assumption, in the absence of prey, that is n equal to 0, the predator population decreases exponentially due to the term minus MP. So from the second equation, when absence of prey, when n equals to 0, so this dPdt equals to minus MP. So obviously from the second equation, dPdt equals to, when n equals to 0, from the second equation dPdt equals to minus MP. So when prey is absent, then dP by P equals to minus dt. So integrating, we get ln P equals to minus T plus ln some constant C. So P equals to C, sorry, M is, here is M, constant, positive constant M into T. So this C into e to the power minus mt. Here M is positive constant and T is time. When T tends to infinity, so this e to the power minus infinity tends to 0. So predator tends to 0. When n is absent, when prey is absent, and predator exponentially decays. So fourth assumption is that the in absence of predator, and absence of predator, when absence of in the absence of first term Rn on the right hand side of one, sorry, fourth assumption, absence of prey, sorry, fourth assumption, in absence of prey, that is n is equal to 0, when n is equal to 0, predator's population, that is P, decreases exponentially due to the term NP. So P is equal to some constant into e to the power minus mt. So when t goes to infinity, so P tends to 0 in absence of prey. The four conditions, four assumptions for this Lotka-Volterra model. And next, the term NP can be thought of representing the N into P, density of prey and density of predator multiplication. Term NP can be thought of representing the conservation of energy from one source to another, and the term CNP is taken from prey and BNP accrues to the predator. So this CNP present in the first equation and BNP present in the second equation. So first equation for the prey's growth dNdt. So this CNP term, CNP affects the first equation dNdt. negative effect on the growth of the prey. This term CNP, due to the negative sign, this term CNP is the negative effect on the growth of the prey. And this term BNP is the positive effect of the growth of the predator, because dPdt is equal to B into N into P, B into N into P minus something. So this is the positive sign. So this term accrues the growth of the predator. Now we non-dimensionalize the system 1, Lotka-Volterra model 1. So for this non-dimensionalization, assume x tau equals to b by m n into n function of t, y is a function of tau equals to c by r, b a function of t, and tau is equal to t into r, and alpha equal to m by r. This tau is the non-dimensional time scale, and this is the n is the density of the prey. So this x represents the non-dimensional densities of the prey, and this p is the densities of the predator. So y represents the non-dimensionalized density of the predator, and tau is the non-dimensionalized time scale. Alpha is the m by r. M by r actually the instinct rate r and the death rate m. Alpha is the proportion. So from this dx d tau, from the first assumption, first term, dx d tau is x is a function of tau. So b by m dn dt into dt d tau. T is a function of tau. So b by m dn dt into dt d tau. So from this tau equal to t into r. So dt d tau equal to 1 by r. So put dt equal to 1 by r. So dx d tau equal to b by mr into dn dt. Similarly, dy d tau equal to c by r dp dt into dt d tau. Now dt d tau equal to 1 by r. So c by r into dp d tau. Then from 1.1 we replace using these non-dimensional quantities. So mr by b dx d tau equals to r into mx b minus this using 1. From the equation 1 you have dn dt equals to dn dt equals to Rn minus Cnp, Rn minus Cnp, Rn minus Cnp. So Rn minus dn dt. So from this equation dn dt equal to m into r by b into dx d tau. So put this, and r into n, the value of n is this. So value of n is equal to m into x by b. So put this m into x by b minus c into n equal to x into m by b, and p equals to r into y by c. So after simplification we get dx d tau equal to x into bracket 1 minus y. And from similarly 1.2, that is equal to dp dt equal to b into np minus m into p. So dp dt equals to, from this dp dt equals to r square by c dy d tau, r square by c dy d tau, and b into value of n and value of p minus m into value of p. So after simplification we get dy d tau equal to alpha this m by r equal to alpha y into bracket x minus 1. So non-dimensional system corresponding to the system 1 is dx theta equal to x into bracket 1 minus y, and second equation is dy theta equals to alpha into y bracket x minus 1. This call it 3. The main advantage of this non-dimensional system is that in the system 1 there are 4 parameters, but in this system we have only one parameter alpha. So it is easy to handle this equation, and this system cannot be solved analytically. So we obtain the behavior of the solution by studying the trajectories of the solution in the xy plane. So we studying the trajectories path of the system, and then we can get the value of xy. Now the equilibrium solution for the system, equilibrium means stable. So this solution is always stable, no effect with time, always stable, always fixed, and the population are not changing with time. Yes, for equilibrium means the population are not, x and y are not changing with the time tau. Here time, non-dimensional time tau. So 3 becomes so dx d tau equals to 0, does not depend on tau. So dx d tau equal to 0 and dy d tau equal to 0, and these the x and y are not changing with time. So obviously dx d tau equal to 0, and so dx d tau equals to 0 and dy d tau equals to 0 for equilibrium solution. For equilibrium solution, where the xy do not change with time, we call the equilibrium solution or steady states. So from this dx d tau equal to 0 and the equation 3, system 3, we have x into bracket 1 minus y equal to 0, and from second equation alpha into y bracket x minus 1 equal to 0. So obviously x equal to 0 and y equal to 0, and x equal to 1 and y equal to 1. So two equilibrium points is are 0 0 and 1 1, 0 0 and 1 1. So x equal to 0 means here x equals to 0 means x means b non-dimensional large quantity, x equals to b by m into n. So since x equals to b by m into n, so from this n equal to m into x by b, and this term n equals to this, and p equals to, since y equal to c by r into p, so from this p equals to r into y by c, this term. So when x equals to 0, y equals to 0, then n equals to 0, p equals to 0, n equals to 0, p equals to 0. So corresponding to the 0 0 solution in terms of the before non-dimensional, in terms of np, we have the equilibrium point is 0 0 also. But when in non-dimensional state in the xy plane, when point is 1 1, and the corresponding point in the np plane is m by b and r by c, put x equal to 1 and y equal to 1. So in the plane np plane, so equilibrium point are 0 0 and m by b comma r by c. The 0 0 solution shows that if both populations are extinct, and they will continue be extinct until an outside factor can change that. So when x equals to 0 and y is equal to 0, no predator, no prey. So these will continue until from outside factor can change the situation. And the second equilibrium solution in the xy plane, that is 0.11, describes an equilibrium when the population of prey is equal to the ratio of the constant m and p. That means x equal to 1, that means n equal to m by b. And the population of predator is a ratio of r and c. That is, when y equals to 1, that means p equals to r by c. So this second equilibrium solution in xy plane describes an equilibrium where population of prey is equal to the ratio of m by b. So population of prey means n is equal to the ratio of m by b. When population of prey is the ratio is equal to m by b, and then we have the equilibrium solution. And population of predator, the ratio is r by c, so we get the equilibrium solution for this. So when population of prey is m by b and when population of predator is r by c, then we get the equilibrium solution. So from second equilibrium solution 1 in the xy plane, we get this two constant m by b and r by c for prey and predator respectively. Now we want to find the trajectories in the xy plane. For that, now dy dx is equal to dy d tau by dx d tau. So from equation 3, put the value of dy d tau, that is equals to dy d tau. So from 3, dy d tau equal to alpha into y bracket x minus 1 and dx d tau equal to x into bracket 1 minus y. So put this, so we get equation 4, dy dx equal to this, which has singular point at 0 0 and 1 1. So if you put 0 0, then the singular point, and also put 1, so denominator is 0. So when put x equal to 0, this denominator is 0, so which has singular points at 0 0, these two equilibrium points, these singular points. By separation of variables from the equation 4, then we get 1 minus y by y into dy into equal to alpha x minus 1 by x into dx. And integrating using initial condition x0 equals to x suffix 0 and y0 equals to y0. This is the initial condition, the initial prey density and initial predator density at time tau equal to 0, non-dimensional time tau equals to 0. So using this initial condition and integrating this, so integrating from y0 to y, from this 1 by y minus 1 into dy and alpha into integrating x0 to x 1 minus 1 by x dx. So we get ln y minus y, y to y, y0 to y, and alpha this x minus ln x from x0 to x. And after simplification, you can get this ln y plus alpha ln x, and this right hand side is all the in terms of all initial conditions x0 y0. So right hand side is fixed and variable is here, and x and y, alpha is parameter. So after simplification you get this term y plus alpha x minus ln x to the power alpha into y equals to y0 plus alpha x0 minus ln x0 to the power alpha y0 y0. So this right hand side is constant. This right hand side is called C0 constant. This right hand side depends on the initial condition x0 and y0. So this is called c0 constant, and the left hand side, this left hand side is a function of xy, is called the function capital H, a function of xy. This equation 5, this capital H equals to alpha x plus y minus ln x to the power alpha into y. So the orbit of the system 3 is given by this hxy equals to c0. We can draw orbit of the system 3, this c0. So this orbit depends on the c0, so that is the depends on the initial conditions x0 and y0 at time tau equal to 0. Now to find the minimum value of the function capital H, we have del H del x equals to 0, del H del y equals to 0. So H is given by 5, so del H del x gives this, and del H del y gives this. So solving this, x equal to 1, y equal to 1. So when x equal to 1, y equal to 1, we get the minimum value of h xy, and this minimum value h at the point 1 1 equals to alpha plus 1 minus ln 1 to the power alpha into 1, that is equal to alpha plus 1. So minimum value of h is alpha plus 1. Alpha is the positive parameter. So hxy obviously greater than h11, which is equal to h minimum. H minimum means alpha plus 1. So hxy is always greater than alpha plus 1. Hence, every orbit of the system 3 is given by the equation hxy equals to c0 for some c0 is greater than alpha plus 1, because hxy is greater than alpha plus 1. Alpha plus 1 is the minimum value of h. And the for given hxy greater than alpha plus 1, the trajectories in the phase plane are closed and implies periodic solution of xy in tau. These trajectories are closed and have a periodic solution in xy. Now, if we change the variable x equals to 1 plus u and y equal to 1 plus b, and then hxy becomes this, put a value, a function h is given by 5. So alpha into x plus y. So alpha into x, x means 1 plus u, plus y means 1 plus b, and alpha into ln x minus ln y. This is equals to c0. So after simplification, you get this alpha into u square by 2 plus b square by 2 equal to c0 minus bracket alpha plus 1, where for small x we know ln 1 plus x equals to x minus x square by 2. Taylor's series expansion for this after conversion two terms due to the term due to small x. So here ln 1 plus u we put here u minus u square by 2, and ln 1 plus b we put here v minus v square by 2. After simplification, you get this. So this c0 is constant, and h means alpha plus 1, this parameter alpha. So alpha is constant. So this represents an ellipse if c0 is greater than h minimum, with equilibrium point 1 1 as its center. So from this we get that trajectories is form of ellipse, and this shows that for h minus c0 minus h minimum small and positive for the orbit are closed curves around the equilibrium point 1 1. Since the solutions run around closed orbit, they must be periodic, and it is easy to see that the maximum pre-population comes 1/4 of a cycle before the maximum predator population. So these the phase trajectories, these the y-axis, and this is the vertical is the y-axis, and horizontal is x-axis. So horizontal x-axis is the prey density, non-dimensional densities, and vertical is y predator densities. And we get for this particularly when h1 equals to 2.1, particular put hc0 is equal to initial condition. So suppose this h1, so suppose h1 is this for particular x0 and y0. So x0 equals to y0 on this line, x equals to y. So this point is x0 y0, x0 equals to y0. So put x0 equals to y0, this point x0 equals to y0. So for this point x0 equals to y0, we get c0 is equal to 2.1. Because for this c0 is equal to 2.1, we get from the equation 4 and this equation, and arrow indicates the with increase time parameter tau, this in this anticlockwise direction. This ways. So this from this closed trajectory we get this point. At this point the prey density is maximum prey density for on this closed curve, and at this point this maximum predator density at this point predator density. Then again this path is if you choose c0, that means c0 means x0 y0. If we choose this first initial condition, this x0 y0, then this prey density and predator density first increase the prey density, and then again decrease the prey density and increase the predator density, and again this is constant, almost constant. Predator density is downwards and prey density is constant, and this along this path prey density increases, predator density is almost constant. So this is the trajectories. Now the arrows denotes the direction of the changes with the increasing time tau, non-dimensional time tau. This model has drawbacks that the solution are not structurally stable, and from this we from Geogebra model, this x density is greater along the x-axis and y-axis is prey, and this is the initial condition. This red point is initial condition. So this represents x0, this point is x0 and this point is y0, x0 y0. So and this time t, this time parameter t, and this first this time parameter t, tau, time parameter tau, this when initial condition starts from this and this x and y and this in this direction and in this direction. So this point represents the this along prey and this predator. Okay, we denotes here x is prey in our node and y is predator. So direction in this way, and this is the prey. So in this notation prey is y, in this notation prey is y. So first increasing time tau, density of prey is decreasing and predator is increasing. When this point is here, so predator is this and this point is prey is this. And next this point is the equilibrium point 11. This point is equilibrium point 11 and this. stop. So in this direction x, although in our note x denotes the prey and y denotes the predator, so in direction, in this clockwise direction, in our note is anti-clockwise notation, and this first graph denotes the prey density changes with time tau, and the second graph denotes the predator density with time tau. So when uh, uh, suppose tau is here, so from that point, then this the predator is maximum height and the prey is the height at the point this height. So and if you start this trajectory lies on this the same path. This red point is the initial condition x0 y0, condition x0 y0. So these beautiful graphs show that the change of the density of prey, and second is red in the density of predator in the model. So this completes our lecture.